But because I'm in a giving mood, you get 5 points anyway. All right? So all of you got quiz 6 correct. And for those of your classmates who aren't here, they get it correct too. So, yeah, absolutely. No, I don't want to make it so this is... I want to reward you coming here, but at the same time, I hope coming here and getting information is it. So... I think I have it working. I suspect part of my issue is dealing with the display itself, whether I extend it or whether I keep it in mirrored mode. So I'm extending it. We're going to try this. I put all of this information into R. So what you'll see here in R is I took every one of these terms in our equation and I built them, all of the matrices, alpha, beta, gammas, and this xi thing. I didn't build xi because that doesn't exist. So I have here matrices. I've got, here's alpha. Alpha is our matrix of main effects, or sorry, our intercepts. So for instance, I'm just plugging in values. Beta 0y, beta 0z, I'm going to just plug in at 10 just for the heck of it. I want to show you how this works to give you a covariance matrix, right? The alpha matrix, which I just showed you the alpha matrix. The next matrix in here was beta itself. It multiplied y. So the beta matrix looks like this. It's a 2 by 2. There's one number in it. That one number happens to be the prediction of y predicting z, the slope for it, right? It's the predictor matrix of endogenous on endogenous variables. The other terms over here, we've got gamma. Gamma is the matrix that holds our slopes for exogenous variables predicting endogenous variables. So that's where you see each of our beta x predicting y and beta x predicting z show up. So gamma is this 2 by 1, it's the column vector itself. And then I have the other terms that we didn't see here. That is, we have our error right here. This is ey and ez go in this squiggle term. Does anyone know what that is? Is that xi? I don't know. Anyway, that thing. That contained the errors, but because these errors have variances to them, the variances were held in something they call the psi matrix. Right? So that psi matrix was 2 by 2. The diagonal elements gave us our residual variances for each of our endogenous variables. The other matrix that was left out was now our covariance matrix for our exogenous variables, and that was what we called phi. And because we only have one, that thing is 1 by 1 itself. So now if we were to go and imagine this was the truth. These were the estimates. This is it, right? These are what we have for our data. We would be able to put together the covariance matrix of all of y with y and y with x and x with x itself to see what it looks like, and we can compare that with the saturated. This should be the saturated matrix, though. If the model fits, this will fit well. So let me show you what happens here. The covariance matrix actually is given by that ugly matrix algebra equation right over here. No, that's not it. That thing right there. Is that not like the ugliest equation you've seen? Or is it up there? That's a formula, right? That is the equation. I'm going to take each of the matrices I created. I'm going to give you this section of the matrix right here. Okay? So I have to take, the first part is I created this I right here, this I term. That is an identity matrix. Remember what an identity matrix was? It's a square symmetric matrix of ones. So I created one. Whoops. It looks like this right here. Identity 2. It's 2 by 2 with ones. Right here. So I have to take the first part, which is identity 2 minus beta. Well, that thing itself, that is what I get, right? That's our matrix, but I have to take the inverse of that. So the inverse of that I can find by taking the solve command. I think. Is that it? No, that can't be it. 1. Did I get this right? Solve. I'm doing something incorrect here. Does anyone know what I'm doing? Okay. I need to chill out, man. I just need to like, you know what I need? I need a hug, or I don't know what it is. I get so irrationally mad with technology today. I don't know what it is. It started last night, actually. R inverse matrix. No, transpose is a different function than inverse. So I want an inverse matrix. Remember what an inverse matrix is, anybody? Look at this. I type it in. Technology. There we go. Yeah, it should be simply solve, right? Solve A is a matrix. So, let me make sure that this is correct. I don't believe that's the inverse of that. So, but let's find out. We can find out by saying a matrix times itself should be, yeah, there it is. That is the inverse matrix. Hey, what do you know? Maybe I was just wrong. Happens a lot. Way to go. So that's our inverse matrix. My goodness. I should be frustrated with me. That thing multiplies this term in the middle. Now that thing is nasty, but we'll make it real quick. We've got gamma times phi times gamma transpose. So in R, the matrix language for multiply is percent times phi. And the transpose function in R is gamma again, T of gamma. So that's gamma phi gamma transpose, but we also need the psi matrix added to this. No, psi matrix to it. So that's what that gamma phi gamma transpose happens to be. This is, I can tell you are all so impressed with this. Sorry. That's that middle term. And at the end of it, we need the transpose of the inverse of I minus beta. All right? So we take this thing again, and we put it in a transpose function. Oh, this is why. There we go. So if these were our parameters, this is what we would expect to find for the variance and covariance matrix of y and z together. Right, that's it, 2 by 2. All right, if I wanted to put that into a bigger matrix, if we wanted to look at the overall covariance matrix itself, this would be, I would call this endo. The endogenous variance variables. I would also, so that's 2 by 2, but if we put all three variables together, we have 3 by 3, so I have to put the exogenous terms back in. That's where these other parts of this matrix show up. The lower diagonal is the simplest one. It's just our matrix of variances and covariances, phi, for our exogenous variables, right? So that's XO is just phi. It's a 1 by 1 term, that thing. Right? So what is left? It's this diagonal, the variances and covariances of y with x and z with x. These are the covariances from it. And again, we find that from our betas and from our gammas. These are our slopes themselves. So that would be solve right here, this term, times gamma times phi. Oops. Percent. There we go. So that's the 2 by 7, and then I take the transpose of that to get the 7 by 2. So that's over in the right corner. This is endo underscore exo equals that thing. And I can do exo underscore endo equals the transpose of endo exo. So what I did all this for may not is kind of questionable, but that's what I get for trying to do this quickly. Is to show you what the entire variance and covariance matrix will look like. And this is the thing that we're going to be comparing the saturated model with. All right? So, let's see. overall is a matrix that's 3, I'm going to call it NA, size 3 by 3. This is just a blank matrix right now. If I do overall 1 to 2 and 1 to 2, say that's equal to endo, that would work. Overall 3, 3 is exo. Overall 1 to 2, 3 is endo-exo. And then this last one where it's 3, 1 to 2. Don't you love my typos? Sorry. I thought when I developed this that it would be good for you to see my progression through all of this so that you can see how all these put together rather than give you something that's all out there by itself. There we go. There it is. So this, if we observe, I just plugged in some toy values for each of these. That's like me saying, I know the truth. If that was the truth, this is what our saturated model covariance matrix would look like. Perfect. Identical. Right? Isn't that cool? So what would happen if we started playing around with some of these numbers? Who wants to volunteer a slope for something? And better yet, I'll just start. I'll start. Let's make the slope of y on z equal to 0. What do you think happens then? All right, so now our numbers start to change a little bit. Right? It went from, what did I have before? Where we had a 144 for this variance here. This is the variance of residual variance of z, or the variance of z. And now it's much smaller because y is not adding variation to it. Let me put back together. Take a look what happens if I change that back, but what if I say the exogenous variable does not predict either of these? Right? Well, if we have no prediction from our exogenous variable, what would this thing look like? Anyone want to guess? There's no covariances between the exogenous variable and the endogenous variables now. Weird, right? So a slope is really doing the same thing as you would think a covariance term might do. That's kind of where I'm getting at here. What about the following? What if I said each of the betas here are slopes? What if I made our slope for y on z, the prediction of z with y, equal to 0? What is this last matrix going to look like now? I guess.
30 becomes a 0.
The 30 becomes a 0 now. And why does the 30 become a 0? Because that slope is treating the covariance between y and z. So watch what happens. So I'm trying to get to this part right here to develop it. So there you have it. 0, 0. Right? So what if I did this model where I took the following? I said, okay, I don't have a direct effect of y on z, right? I have a 0 here. What about an indirect effect? We're an indirect, right? Like the, what if I put in here a residual covariance between y and z? Where do you think that shows up on this analysis right here? Right? I've just zeroed out the regression rate. There's no direct effect. Right? So if I add back a residual covariance between y and z, where does it go here? It's going to go between the correlation between y and z and stuff. So watch this. If I add that to it, that is this psi matrix right here. So if I say psi 1, 2, oh, let's make it 30. Watch what'll happen. There's our 30 again. All right? So what we've just done with all of this is I'm trying to show you this. Every model has a structure. Every model implies a structure, right? this, when we know all of the parameters, we know the structure exactly. Our saturated model will look like this. And actually, this model is just identified, so our saturated model will always look like this. But each model parameter comes from each of these places in the analysis itself. Is this helpful at all to see all of the combination? No, maybe yes. So in your homework last week, we got into the Model 3 and Model 4. In Model 3, I asked you to go and translate everything from Models 1 and 2 into a supermodel. First of all, let me back up. When I looked at that analysis, I thought to myself, hey, here's two models in a paper. These two models have different endogenous variables, or different fully endogenous variables, but slightly, they have different, they have the same exogenous variables, but different endogenous variables. Why are there two models? Let me just spit it out. Why are there two models? We could put together one by itself and come up with an answer. Did you think that when you saw it? Probably didn't take that level of abstraction. You're probably like, okay, I gotta figure this out, I gotta figure that out. When I saw that paper, I saw that. Do you ever see papers in the field where they do one analysis here and they answer this question, they do a separate analysis altogether and they answer this question? Right? That is why, one of the reasons I picked this paper. Don't ever do that. Right? If you have a set of variables, when you start doing multiple analyses and so forth, particularly in regression, it's egregious. The path analysis is like a regression. All the variables work together in a complex multivariate way. When you take a segment of them and do one analysis, and you take another non-overlapping segment or overlapping segment and do another analysis, you're not getting the full picture. Right? It may be the case that some descriptions are different when you do one analysis rather than you do two. So one of the reasons I see two analyses in a paper with the same types of variables in the same data, same variables, I'm like, what are you trying to hide? That's the first question, right? One of the ways this pops up sometimes in my job where I work as a faculty member is where I, when you get to dissertation stage, somebody comes to me and says, I need you to be on my committee. And it's usually somebody who's not in my program. My program is different. They're like, you, because you're in my program. But it's someone from, let's pick a great department. Who no, what's it? Political science? Sorry?
Educational policy.
Educational policy. And they're like, I need you to be on my committee, and usually it's because you do statistics. But they'll have a list of research questions, and they'll do a separate regression analysis for each from the same data. Right? And sometimes with different dependent variables. And the thing that's lost from that is, with one regression analysis, all the dependent variables and all the independent variables being different, when you put them all in the same analysis, if the independent variables are correlated, as they often are, they will affect the other results in the analysis, right? And it's from this type of matrix that's happening. So I saw that and I'm like, we got to do one analysis, right? And not only do we need to do one analysis, it's not that. I mean, it's a challenge, particularly when you're learning path analysis. It's a challenge to do this. But you think about it, you're doing this as a homework. We would expect somebody to publish a paper to be able to do this publishing a paper, right? So that's why I put that as the homework. So, okay, please, don't ever do two analyses. Build one. Right? If you do two analyses, make them separate sets of data. That's it. So build one. Build it all together. You put this together, and all of a sudden your total number of variables goes from, I believe, was it 5 in each Model 1 and 5 in Model 2 to, was it 7 or 8? I can't remember exactly. 8, thank you. So what happens to the total number of parameters that you can have in an analysis when you go from 5 to 8? Let's think about it in terms of the mean vector. It has 3 more terms, right? The covariance matrix, by the way, the number of parameters in the covariance matrix, if you have n variables, the number of parameters in the covariance matrix is n times n plus 1 divided by 2. So that's the covariance matrix parameters if I add to it the number of means. So I have n times n plus 1 over 2 to it. I could probably put it all in one equation, but just to kind of see where each part comes from. We get it. So with 5 params, n equals 5, that gives us in a saturated model, 20 parameters. Right, that's the limit to what we can get to. If I switch that to 8, we have 44. Right? So we have to go describe a lot more information in one analysis to make this work. The bigger picture is when you have the smaller the number of parameters you have in a covariance matrix, right? This is the number of total parameters in a covariance matrix and the mean vector. By the way, bless you, whoever it is. I've said it once, now I feel like I can't not say it because I feel like, I don't want you to think that I hate you or something like that. I try to be equal here. I try to treat each of you equal except for Megan. She's terrible. I pick on my advisees a little bit more. But it's easier to have a model fit when you have degrees of freedom that are small, right? So if we had 5 parameters, we have a total of 20 model things that we have to kind of account for. With 8 variables, we have 44 things that we account for. What should happen is we'll have more degrees of freedom left over from our model in the 8 than we will have with the 5. Those more degrees of freedom are essentially like saying those are empty spots in this variance and covariance matrix, or those are, those linear equations where some of our parameters are going to have to stretch and bend against it. So sometimes you'll see people present multiple models. I'm not saying this about the author, I didn't do this, otherwise when I look at this, it's a way of hiding mistakes, right? They'll have multiple models. Both of them had an RMSEA of 0.03, which was good. You remember reading that? Maybe that helped a little bit too. So look at that, model 1 and model 2 fit well. What happened in model 3 for your analysis? What was your RMSEA? Do you remember? Not pretty. 0.092, something like that? Something like that. So 0.092 happened, and I think that was expected. I don't have these people's data, so I simulated data based on their results. So this is to happen. So I'm really not trying to throw shade at this paper itself. I would if I was a reviewer or editor. I probably would have said do one analysis, and they would have done one analysis. And they probably would have done the steps that you just see right here. But then what? What do we do? Okay, well it doesn't fit well. The question is, where does it not fit? Right? So you want to get a residual covariance matrix, and heck, why don't I just grab that real quick? I can pull this up. You can't see what I'm doing. It will be here, I promise. Here we go. No, I can't get back to it. There we go. So having the screens on top of each other, but the way to get to it with my mouse is on the right side of my screen and the left side of it is just killing me also. I just need to chill. Maybe I need just, I know what I need. I need to go to the bar after this. There we go. So, maybe not the bar. Okay, so here's what's happening in all of the output itself. If you go back up to the line of code that asks for, I have the residual model fit here. This was the difference between, this is our normalized residual. So there's all the variables in our analysis between models in model 3. And this is taking that model implied covariance matrix, which you saw us build, right? It took all the slopes, it took all the variances for the endogenous variables, it took the covariances for the endogenous variables. It took the exogenous variance and the exogenous covariances all into consideration. And then it compared it with the saturated model that had all 44 parameters, 36 of which came from the covariance. And we looked for the two biggest numbers. Right? And we saw a number of 3.72 here between motive to communicate and motive to use. And we saw a number of 4.229 between number existing and number new. And those were all endogenous variables. Right? So to modify this analysis, we have several options. Right? The modification for it could have come from adding direct effects. Right? If we wanted to improve the fit of a residual matrix like this between two variables, we could add a direct effect between the variables. Right? We could say motives to communicate with current existing friends predicts motives to make new friends. Right? Or we could do the opposite. Motives to make new friends predicts motives to communicate with existing friends. Same thing over here with, or option 3, excuse me, we could add a residual covariance between the two of them. We could add a residual covariance because the two of them did not have a link between them directly just yet, right? We look at our syntax for model 3, we see here that motive Tom and motive new do not predict each other up in the syntax for each of the endogenous variable regressions. And then the double tilde, the residual covariances, don't predict each other as well. So when I asked you to go and add then to this, actually let me back up. I also said, oh, look at the modification indices. And what I was trying to do was link these modification indices that you would get to that residual covariance matrix, right? And sure enough, in the residual covariance matrix, the numbers in the modification indices applied to the variables that we saw the biggest residual covariances to, right? So modification indices are trying to provide the statistical side of what the residual covariance matrix is telling in a path analysis, right, where the misfit happens. And it's trying to tell you you could add this parameter right here. Or you could add this parameter right here, right? Or, there it is, there's a motive new and motive number existing. You could add direct effects, you could and you'll see the direct effects, the numbers are floating around a little bit, even though those are identical models. I told you before, if I added the direct effect for number existing and number new, or I added a residual or a direct effect in the opposite direction, they should give you the same likelihoods. The modification index is a little whack. It doesn't give you the exact number, but if you do this in practice, you can only pick one. So in homework, I asked you to add the two effects that were, normally you would add them one at a time and that would get better. And I asked you to add them as residual covariances, right? So here it is with both of them added. And now when you add those to your analysis, you should see that the model fit was much improved. All right, it went from 0.092 for the RMSEA down to 0.034, which then brought about happy feelings, publications. But what I was trying to say is, okay, so the model that they had done, the two models they had done weren't really that different, and when you added things or put them together, you didn't get really that different of results. But it is the case that results may change more. When you have really bad model fits, 0.098, 0.092, or whatever the Model 3's RMSEA, people publish with that all the time. It didn't change the results a whole lot. But it is the case sometimes when you have bad model fit, your results do get bad. So, anyway, big picture, we can do all this with one model, and we can make the model fit better by adding parameters or moving things around. Okay, how are we doing? Path analysis still? Questions? Yes, Vinay.
So when you're going through looking at the model, you try, you take one, but it has to pick the one where it's kind of going against the grain, and it works. You reviewers kind of look at it like, whoa.
Sometimes.
You could say, you're going against the grain, that's not recurring, that's not me.
That's exactly. Sometimes reviewers don't even look at all. A bigger critique from reviewers is that modification indices, if you think about that whole table, every one of those is like a hypothesis test, right? So everyone, it's like a multiple testing problem. So you could have false positives show up here, right? Where you have a modification index with a big number saying, oh, this parameter right here is non-zero. Would that really be a type 1 error rate? It thinks it's non-zero, but it's an error. It's really zero statistic. So one of the bigger issues is this is sort of cheating or too many tests. You're capitalizing on tests. So for your analysis itself, for this sample, for this, especially if you have a small sample size, you may find that, yeah, I need to add this one parameter. But then, you run this, and because Megan, is contrarian the way she is, and she's in your program, she'll be like, well, let me go and do your study with a new sample. So Megan collects the sample, and she doesn't find in her modification index that she needs to add that. She now needs to add this one. Right? The stability of the result becomes important. So it's possible. So, sorry, Megan, you're not really that much of a contrarian. I'm picking on Megan. Megan wasn't here last week, so I couldn't pick on her. She's getting over. No. So Megan was too good for class, and so I had to find a way to pick up on her. I'm really digging a hole. I need to stop. None of this is true. I'm joking. Megan, I'm sorry.
I'm great.
You're great. Megan's great. And does that help you answer your question?
Actually, now I've got a follow-up.
Yes, please. That's fantastic.
With, I guess it's like, we'll start off with 822 stuff.
Mm-hmm. 822 is Billy's class. Scale. Got it.
Where you can drop items
Mhm.
with your alpha
Mhm.
to a point, and that sort of has where's the cutoff with that? There's the same thing that applies with these models. You're adding these things one at a time. Okay, if I add this, it'll go a little higher. If I go up this, is there a sort of place where there's a cutoff, where there's like, you've gone too far?
The question would come from is every time you add one, you have a chance you're adding one that really shouldn't be there. So you draw the question as to whether or not, if you didn't think of this ahead of time, you're now changing your hypotheses a little bit. You start with this initial hypothesis that didn't fit, you got to tweak it. Oh yeah, I didn't add this correlation, so I'll add that. Right? So no, there's no cutoff as to where you can get to the saturated model. You have equal parameters in your model that is in the saturated model, then you can't get any better. Right? But what happens to be there may not be, it may not, every one you add may not be legitimate to add in truth. Right? It's just your data suggests it should be added. So where do you draw the line? I don't know. Right? Similar discussion came in that, if you think about this as, where have we seen in statistics other cases where we have tons of hypothesis tests? Post hoc tests in analysis of variance. Right? So you've got an omnibus test for a factor in ANOVA, and you say it's significant. You're like, okay, great. Which pair of means is different? And so you've got all sorts of mean comparisons and so forth. Same critique there that you see here. Personally, I think you add them. I add them and argue for you. A lot of people will do too in the path analysis, particularly if they're the residual covariances seem to be less arguable because you're saying, yeah, I don't understand why these things. I'm not explaining that these things covary. They just covary, and I need to account for that covariation. Yeah, good.
You mentioned the post hoc test, and those usually have a defense like you're going through on your
Yeah,
where you cut your alpha, you cut your significance level.
Can you do that here too?
Okay, thank you.
Yeah, so that MI or MI scale is a chi-square. It would come from, if you did a likelihood ratio test of your model that gave you the model fit that you just had, and the model where you add that one parameter to it. Right? So likelihood ratio test, you put it in the ANOVA function, right? So that's what you would expect the chi-square value to be. That's the hypothesis test. You can compare that with a chi-square distribution with 1 degree of freedom. A chi-square with 1 degree of freedom has a critical value of 3.84 at an alpha of 0.05. But maybe you want your alpha to be lower than 0.05. Maybe you don't want, you've got so many tests, maybe you want it to be 0.005 or 0.001. That's equivalent to saying, I'm only going to look at modification indices that have a number that's bigger than 15 or 20 or 100 or whatever. Right? You can just set that to be a limit where you wouldn't even consider them otherwise. And that will, in theory, protect you from picking too many of them. So just like you would the Bonferroni correction, which would change the p-value, your p-value here is the type 1 error critical value for a chi-square distribution. Is this helpful at all? Other questions on this homework? It's a good name.
This is actually not really, but probably obviously specific to me.
Okay.
I saw your syntax with the residual covariance, and I've seen a couple of others, they only had 4 terms. When I 4 terms,
Mm-hmm.
I did not get the same number.
Mhm.
It wasn't until I essentially copied the lecture 5 syntax with all the 0 times,
Yeah.
and it took the zeros off those 2
Yeah,
numbers.
that's right.
Before,
That's right.
and then it finally did it.
The reason for it is it adds, if you don't zero all of them out, it adds a sum of them to your model.
But I didn't see yours zeroed out in your syntax.
In my syntax, I thought it was. I zeroed some of them out. So here, let me go back in time here. Let's imagine I do this analysis right here, and I comment out. This is model 3, and I comment these out, right? And let's see here. You guys are distracting. What's funny? The two of them are joking with each other, and they're not wanting to share it with us. You're not in it at all. I find this distracting. Pardon me. So, in this, what you end up seeing is the following. I zeroed out those, and look how many that I got out of it. I end up getting 6. Right? And that's where counting helps you. When you do a model, count up the number of parameters that should be there. And then when you estimate the model, check that the number of free parameters is equal to what you counted. Because if you don't do that, sometimes software will be trying to be nice, add them in for you. The way that this is working in Levon is what it's adding for you is the let's see if I can get a picture of the path diagram here. For all of the variables where you have this path diagram's terrible. It's hard to see here. It's adding residual covariances between variables that are endogenous but don't predict other endogenous variables. Right? So you essentially remember we had in model 1 there were 2 endogenous variables that didn't predict anything else, and in model 2 there were 2 endogenous variables that didn't predict anything else. It adds the covariance between those for whatever reason. It's just saying, hey, you're not doing anything with these, I'm going to add the covariance term to it. Right? It's treating them like you would in a multivariate regression. But, does that help? Okay. Next questions. Other questions? All right. Next, let's do this. Now that was path analysis. Last week we introduced factor analysis. Factor analysis is a little bit different in that it takes, here I'll just draw on the board for this. But if we have 3 variables, we'll call this y1, y2, and y3. Right? We have our 3 variables here. Let's imagine this is like we had in our first example. Actually, our first example had x, y, and z. Call them x, y, and z again, right? Now, the path diagram looks like this. We have a factor, and it's predicting these 3 variables. Right? So, in this type of analysis, we have 3 endogenous variables now. Right? Those 3 endogenous variables, we can draw out equations for each. Right? We could say this is beta 0x, beta 0y. I didn't use this notation before, but let's just put it in path model terms because we're talking about path analysis. And beta 0 z. Right? So there's our beta zeros for each. Then we would have the beta of f predicting x times f. We'd have the beta for f predicting y. And we have the beta for f predicting z. For all 3 of those. And then we would have error for x, error for y, and error for z. Okay, so we have all three of those present. So what this ends up saying, this is, again, like we would think about a path analysis. The only difference is that f would be an exogenous variable, but we never observe it. Right? So that changes a lot. It's like, oh yeah, if we had observed f, our saturated model's covariance matrix would be 4 by 4, right? Which would have 4 times 5 is 20 divided by 2, 10 parameters in it, right? There's 10 values in that covariance matrix. But really, we only have 3. So we only have a 3 by 3 covariance matrix. We've only observed 3 variables. We can't add something we didn't observe to it. So the 3 by 3 gives us 6 parameters. Right? So these betas right here, these are called factor loadings. Right? Right, those are regression slopes if we had observed the factor and then predicted each outcome with the factor itself. And just like we saw in R here, when I look at the overall covariance matrix, remember which terms go where. Each of these factor loadings, because they're the slopes, go into our covariance matrix of our endogenous variables. They all show up there. So a lot of times we talk about the covariance matrix with it as well. So this ties us back together again with the path analysis. These terms right here are called item intercepts. Item intercepts are, if we think of these as items of a survey, they are what we would predict the item to be when the factor is equal to 0. A lot of times that's the meaning, actually most of the time we set the factor mean to 0, so that's right at the factor mean itself. Right. And finally, each of our error terms, like error for x, will still follow a normal distribution with the mean of 0. And if this was a path analysis, we would call this a residual variance for x. But now it goes by another name, which is unique variance. Right? So really the weird thing about factor analysis is we've just taken all the terms that we knew in regression and relabeled them to something else. But they all stand for the same thing. This sigma squared error would be if we observed the factor and predicted x with it, it would be how much is left over or how far off are we in our prediction. And the variance for it represents how much variation there is across all of our observations that we found. So far, so good? Questions? Comments? Okay, so to do factor analysis, we have to set the scale of the factor. We set the scale of the factor by setting the mean and the variance. Right? So the factor, we always, in this class, we'll call the factor following a normal distribution, but we need to either set or estimate some of these terms. Right? So the factor mean, we set to 0 usually. And for the factor variance, if we want to estimate it, we have to set one of the factor loadings to a constant. We typically pick the constant of 1 itself. All right. So now I'm going old school. I'm going to turn off my screen, and I'm going to talk about what happens here when we set that. How does that set the factor variance? Boom. Okay, so if this is our let's look at our covariance matrix of x, y, and z again. This is what we have to work with in terms of the variables, the variables, the things, the numbers, and then the unknowns, the system of equations that we have to set up. Right? We have sigma squared x, sigma squared y, and sigma squared z. We have sigma xy, sigma xz, and sigma yz. Now that's our lower triangle of that covariance matrix, right? Our factor model does the following. It specifies that this covariance matrix is a function of the factor loadings, or in this what we would call the same slopes that we saw before. It's the same function that you saw in path analysis, right? What does it involve? Slopes of the endogenous variables, right? So those are factor loadings. Variances of the endogenous variables, those are residual variances or unique variances. Covariances of those things, right, which we didn't talk about yet, but we'll talk about next week. Something about exogenous. Well, we didn't observe the exogenous variable, so it can't be there. Actually, it is. It's there, the factor variance. And then covariance, there's only one in our analysis so far. So what we can do is the following. We can say sigma squared x, y, and z. We can take each one of these and specify what the model thinks each of these should be. Right? In a factor analysis model, I mentioned this, I went through it sort of quick last week, but let me describe it again. The variances are found by taking the loading, or I'll just do it in betas here, but last week we did lambdas for it. It's the slope for that item of the factor, predicting that item, times the factor's variance plus the residual variance for that item. This is factor loading times factor variance plus unique variance. Last week it looked like this. Lambda for x, sigma squared f plus psi squared for x. Psi squared is what we usually use for the residual variances or unique variances. And if you follow the notation book that I just pulled up, the matrix psi was the residual variance covariance for that company. But to identify this, we went and turned this thing equal to 1. So I'm going to take that thing off. So I have it for y. And I have it for z. Right there. So sigma xy, sigma x to z, and sigma y, z show up. All three. Okay? So what do these terms happen to be? Last week, again, I mentioned it quick. I'll just gloss over what it is now. Beta, it's the product of the slopes for each of the variables with the factor times the factor variance. So this would be beta x for the factor. I got this right. Beta for the factor x, beta for the factor y, sigma squared f. Now we took beta f and turned that into a 1, so that just shows up. Right? This is beta f x beta f z sigma squared f. That thing's a 1. This is beta f y beta f z sigma squared. So where all so we have now 6 equations. And how many unknown terms do we have? We have 1 variance to the factor, 2 slopes, 1, 2, 3, 6 residual or unique variance. All right, so we actually have 6 things that we could know, 6 things that we don't know. So we could solve for this and go in and plug in each of the terms if we wanted. Right? But I won't. This is what's happening in factor analysis. Our factor analysis, if we were to go and put the slope for the first variable in, look what would happen. We have to fix, I talked about having to fix the factor variance. If I set the factor variance to 1, but estimated the slope, the factor variances would go away. But here we'd have beta fx, our slope for the first, or the factor loading here, and it would show up down here. But again, we have 6 equations and 6 unknowns. These models are identical. So factor analysis works similar to path analysis. It's just the factor itself goes away. How we get to know what each of these are follows the same algebra that I didn't show you So I pulled up the book from the Kaplan book to find the result. There's a matrix product that shows up that gives all this. Question? Is weird? Catching up? So again, just like path analysis, we figure out what our parameters are. It implies a covariance matrix that we go and predict, or that we go and compare with our saturated model covariance matrix. So, questions? With 3 variables, it's just identified. Right? So remember we talked about to identify a factor we needed 3 things. Right? So, if you're creating a survey, your model fit for a 3 variable factor is identical. Ironically though, the model that has this specified, I'm going to put 2 models up here. All right, so here's model 1, or model 1. This is going to be model 1 star. All right, is one where I just let these all these be correlated. Right here. Right? Those 2 models are equivalent. So when you create a factor with 3 variables, even though the model fits perfect, you can't actually test to see the factors there. You created something that's equivalent to a model where all 3 variables are correlated. What happens if you want to test if a factor's there? You have to add a 4th variable. Yeah. You add that 4th variable. Now this covariance matrix has 10 things in it again. Right. The number of parameters you have 1, 2, 3 factor loadings, a factor variance, that's 4 residual variances, there's 8 things. But you have 10 equations. Right. The opposite to that is putting in all the variances and covariances right here. So, if you want to build a study, if you want to say, hey, I believe that self-esteem is measured by these 3 things, it's possible it's measured by those 3 things. It's also possible that those 3 things correlate but don't measure self-esteem. How's that? But if you had a 4th item, and you said, hey, this 4th item, these 4 items measure self-esteem, you can test to see whether it measures self-esteem or not. You can falsify that hypothesis. In the same way that we couldn't figure out whether it was a direct effect going one way or the other way or an indirect between, 3 versus 4 did the same thing. So in building path analysis and putting that first in our class, I really wanted to try to set up the same rigor, the same thought process with factor analysis. Sometimes when people teach factor analysis or they teach scale building, it's a completely different entity. Right? It's out there. We talk about dropping items so the alpha goes up, and we haven't even talked about alpha yet or anything else. In our world, right, this is the scale right here. That's our scale. By saying we have items of the scale, we are forming a testable hypothesis. If our model doesn't fit, we've just rejected that. This is not a scale. There's not one factor that underlies this. Right? So that's kind of not the same. It's the same world. It really is. It's putting a mathematical and statistical rigor to the process of scale building. 822? Classical test theory? Oh, that was last year. 921's classical test theory. How many of you are in that class this year? Classical test theory is a factor analysis where we said all the items. A classical test theory, the idea is that you add each of these numbers together and you get the total score. Classical true score theory comes out. What we're going to see after we get through SEM is that classical test theory is a series of constraints on our regression in a factor analysis. In fact, it's saying that each of the factor loadings are equal. That's a testable hypothesis too. We know how to test that in Lavant, right? Whenever you constrain things to be equal, do you remember that? You put the number there times the effect. So if we wanted to say, well, okay, I've got, pick your favorite professor that never did factor analysis and they just add things together. They're going to add these four things together. You can say, wait a minute, we can test whether or not that should be true. Right? We take a model where we go and set all the factor loadings equal to 1, and we estimate it, and we see if it fits. If it doesn't fit, it can't be true. We can free the factor loadings, or at least all but one of them, if we estimate the factor variance. We can test that. That might fit. The classical test theory fits under this perspective as well. So what you're learning about in classical test theory is essentially saying, I'm going to take each item and weight the influence of the factor on each equal. Anyone ever add things together? You ever add things up? I'm okay. I do. I do all the time. All right? Little did you know, when you add things up, you're doing this. You're doing a factor analysis, you're doing a CFA, but you're going one step further. Not only are you saying the things that you're adding up all measure one thing, you're going and saying, I know the factor loadings are all equal too. That's the model you are implying by adding things up. We'll see after spring break. Should fatherhood not, do me in? We'll see how well I can describe this to you to try to get that point across. But what that really means is all the times you've added things up, you could test whether that was justified. If you were adding it up and this hypothesis, this test failed, you were then using a result that was not fitting, essentially. So your result may be causing issues. So what we end up doing in structural equation modeling is we just test, we make sure this model fits, and then we use F in an analysis simultaneously, like with the path analysis, so we don't have to add things up, we don't have to put error back away, it's all compartmentalized into one nice one. Those of you who aren't in the classical test theory class, I hear it's wonderful. The coefficient alpha, we can actually determine what coefficient alpha is by our factor load. How about that? There's your one-to-one correspondence, or classical test theory for factoring out. Coefficient alpha comes from this formula of factor loadings and actually residual variances, unique variances. If you take that formula with residual variances, factor loadings, you can then say, oh, that's coefficient alpha. That's if all the factor loadings were equal. But if they're unequal, the formula still holds. You can give a reliability for a sum score, even if factor loadings aren't equal. Sometimes called coefficient omega. If the model fits, it's pretty much the same. If the model does, alpha is actually higher. Lower than that. The model doesn't fit. That alpha that you're adding up, not your reliability. Way better than your reliability. It is the best case reliability should the model fit. So every time you do an alpha, oh yeah, I'm doing this model underneath it, and it's actually I'm using it indirectly using the factor loadings for it. The model doesn't fit the factor loadings are off, so therefore alpha is off. I hope this helped. Today we got a couple minutes. What I was trying to do was synthesize what we've done to this point. Did it help a little bit? Slow down, talk about it. Next week we're going to talk about factor analysis some more. And we're going to use factor analysis to build a scale. Right, we're going to take a set of items and build it. Again, I'll grade your homework tomorrow morning or Friday morning and send it back to you. And you'll have it due, revisions due for homework 3 next Wednesday. Then the following, next Wednesday we have class, and the following is spring break. There is a homework 4. You could actually do it now. It is doing what we're doing next week, but it's building a scale. It's due after the week after spring break. So you still have plenty of time to deal with it. I'm not going to change that. It's comparatively, it's a lot less trying to figure things out. The homework says, run this factor analysis with 12 items, And then somehow magically it says drop these items. That magic part of dropping is what we went through last week, and really it's BS. So I just wanted to get you to see a factor analysis model that fits. The statistical dropping of items in factor analysis happens all the time, but it changes what the scale is. So it's kind of good. So thank you for paying attention. I will, if you have questions about things that we've done, please let me know. I'm happy to help. I want you to understand that, and really no question is, don't feel shy about asking. There's no such thing as a low-level question or a stupid question or anything like that. I want to help you. You can do this. So thank you all.